Okay, so good morning, no? So to one and all, it is uh, it is a pleasant morning to everybody or a pleasant day to everyone. No? So we will now go into this lesson on light as electromagnetic wave. No? There's a video for this one, no, which was rendered by Professor Dave, no, and I hope you watch that video. No? It's a very important video. It speaks about the electromagnetic spectrum, no? And this concept of the electromagnetic wave was combined, no? So we can actually connect together the lesson that we had on magnetism, on electric field, on our magnetic induction or electromagnetic induction to the principle of light, because this wave, no, that comes from the sun, no, in the form of this visible light is actually, no, one electric and one magnetic wave, no? So it's a combination of this electric and magnetic wave, which we eventually call as electromagnetic wave, no? So it has a very broad spectrum. When I say a very broad spectrum, there are a lot of other rays that are inside it, no? Not only the visible light of the sun, no? So the one that we can notice with our eye is the visible light of the sun, no? But other than that, no, there are actually no other rays or parts of the wave there that we may not observe with our eye, no? And moving on, no? So we have this broad, no, electromagnetic. We call it as a spectrum because there are other portions there of the wave that is not only light. Light has a specific, or the visible light or the white light has a very specific wavelength, no? So may wavelength na siya that's around 400 nanometer to 700 nanometer, and that's the only one that can be, no, observed by our eye, no? But the rest of that, no, those that falls below that wavelength and those that are above that wavelength, no, we can no longer, no, notice it, no? But they are there, no? So that's why we call it as a spectrum. So it is considered both as a wave, ang light, no, and at some point, no, they also consider it as a particle, no? So they say light, it has a dual nature, dual characteristic. It behaves like a wave, no. It undergoes reflection, refraction, all these characteristics of a wave, and at the same time, no, we can think of them as something like an atom, no? So an atom is completely separate from other atoms, no? So kung pares pa sang balas, no, if you have a sand in your hand, no, the sand there looks like a lump of matter, but if you can actually separate it one from the other, there's actually, no, a single grain of sand, no? So light could also be thought of as a kind of particle, no? So light is a visible form of energy, no? So usually energy, we can feel it, no? We can use it, no, like electrical energy, no? But this form of energy, no, we can actually see it with our eye, no, especially the portion of the white light or the visible light. Now most of the energy that surrounds this wave, no, we call as electromagnetic wave, is invisible, no? Most of it, no? But there's this portion of this visible light, no, that can be transformed into different colors, no? So that's what we call as the, no, white light or the visible light. Now here's the maybe, no, the range of frequency or the range of wavelength, no? So we call it as a magnetic spectrum again because there are a lot more, no? So the one in the middle, no, the one with colors, is known as the visible light, no? This is part of the electromagnetic wave, no? So the electromagnetic wave has so many spectrums there. So you have the gamma rays, no, that are very short in wavelength, no, but they have a very high frequency, no? And this is how the energy is changing, no? So the energy is not the same, no? So there are those part of this wave that have a very high energy, and those that have a very minimal amount of energy. No? So, but the one in the middle, that's what we call as the visible light. No? Its range of wavelength. I'm very sorry that I got cut again. So, going back now, so this is what we were discussing just a moment ago. So we were here already. So this is again the portion of the wave that has a kind of certain length of a varied spectrum of light, and the one that has the longest probably wavelength is the radio waves, and the shortest one are those that are considered as cosmic or gamma rays. So their energy now is changing, their wavelength is also changing, just like its frequency. So the energy and the frequency usually goes together. However, the wavelength is kind of opposite. So as you decrease the wavelength, its energy is somehow increasing. So to some extent, the gamma rays are those that have a very high energy, and they are quite lethal or dangerous to us. So I think now this is the portion of the wavelength from the sun that we do not really need. We have to be shielded from these cosmic rays because they are kind of they are really not dangerous to us. So here are again some forms since we are talking of a wave, guys. So a wave has a wavelength. So those that are in phase points are those points that goes together. Those points that move in opposite directions are called as out of phase points. So the distance between these two in phase points is known as wavelength. So those that are at the top are called crests. Those that are at the bottom are called trough. But the farthest point from the equilibrium line, this dashed line is the equilibrium position of the wave, and the farthest point at the highest is known as your amplitude. So amplitude can go either downward or it can go upward from the equilibrium line to the farthest point in the wave. So your trough, if you measure it from the equilibrium line to the trough, may be considered also as amplitude. And usually the amplitude dictates the energy of the wave. The higher is this amplitude, then the greater is the energy of the given wave. Now, some waves have shorter wavelengths. So maybe this one is kind of very near to each other. But when you have very short wavelengths, then you'll notice that the wave will be repeating more often, and then therefore it will have a higher frequency. Now, if it's a kind of sound, guys, the sound wave that has a higher frequency usually sounds with a higher pitch. But that's with sound. This is about light. So light may also be in this manner. Now we call this one before as a transverse wave. So the wave that its particles is moving perpendicular relative to the wave motion. So if the wave motion travels from left to right, the particles of the wave there is simply moving up and down. Okay, now we have next our transverse wave again. So we mentioned it just moments ago. So the motion, the direction of the motion of the wave, and the particles that are moving are perpendicular. So if you recall the water waves that we have in the ocean, it's also a kind of a transverse wave. So another kind of wave, we have the longitudinal wave. So the thing about our electromagnetic wave is that there is a blue this colored blue a wave which we call as the magnetic field moves perpendicular also to the magnetic field. No? So we realize that whenever there is current, no, or electricity, we realize nga there's also a possibility that a magnetic field is set up. No? So just like when we talk about magnetic induction, when we move a magnet, no, into a wire, guys, we notice that current is created. No? So in the same way, if there is an electric field, no, then a magnetic field is also set up. No? So this wave eventually became known as the electromagnetic wave. And I think, no, the one who created an equation that related these two was this very bright scientist called, his name was James Clerk Maxwell. No? He integrated, no, the concept of this magnetic and electromagnetic waves into, no, one grand principle. No? Okay, now how fast is this electromagnetic wave is moving? Now, in terms of kilometers per second, no, it is equivalent to 300,000 kilometers per second, no? Or you can write it as 300, no, million, no, meters per second. No? So how fast it can traverse the surface of the Earth? It can cover it, no, 8 times, no? Okay, so that's how fast is light, no? So the speed of light, no, and the speed of electromagnetic waves are the same because they are, no, light is part of the electromagnetic wave. No? So eventually, no, they will have a similar value. No? Now there were people who attempted to measure the speed of light, no, even way back. No? And we have Romer, no, as one of those person. So they although they have a very crude way of measuring speed, no, or the speed of light, no, they attempted, no, and they got a value that's quite close, no, but of course, no, with a huge error, of course, no, but their attempt was, no, not really that futile, no, but they got some approximations there, no, that are quite acceptable, no, given the time, no, that they were doing the measurements, no. Well, if we will think about the speed of light, it's kind of fast. But if we will look at distances, guys, no, that are like light years, no, distances between galaxies, then you'll notice that light may not be that fast after all. No? So probably light will be traveling for a year in order to reach one point. No, but of course, no, that's a relative concept because the distance that we are talking now are very, very great distances. No. So, but what they believe, no, or what we believe to be true right now is that light is the fastest thing in the universe, no? So nothing can still beat light, no? And according to this relative theory of relativity or the special theory of relativity of Einstein, no, light is traveling, no, at a constant speed, no? So regardless whether you put light there, no, on top of a moving car, no, light will still travel equally the same. No? So it will not be a little bit faster, a little bit slower. No? Light is believed to be, no, moving in constant speed. No? Now, light again, no, is either considered as a wave or a particle. So when we think of it as a particle, no, because we realize that light is eventually reflecting or refracting, no? And that's a behavior of a wave. No? But when you consider light to be some kind of individual particles, no, or quanta, no, then they observe that it can, no, it can repel an electron. No? So if you have a beam of light and you let it, no, be concentrated on some kind of particles, no, like some electrons, no, then these particles of the wave can influence the electrons to travel in a different direction. And it can kind of repel or it can affect, no, other very minute particles also. No? So they call it as a photoelectric effect. No? So if light is merely a wave, probably it may not, no, it may not influence, no, other small particles. No? But somehow, no, since it can redirect, no, it can knock off, no, electrons, no, to some degree, then light could have, no, a particle within it, no? And we call the particles of light there as photons, no? So these photons, no, that are undergoing or can perform, no, this thing that we call as photoelectric effect, no? So again, no, beaming light, no, in some electrons will probably, no, change the course of these electrons, no? So again, no, that is only, no, possible when light, no, is also, no, some sort of a particle, no? So this this study of the quantum physics, guys, no? So we think of things as, no, being an actual particle, no? So there are ideas that some things are just kind of continuous, no, that they could not be broken down into some heaps, no, that you can count them, no. uh, but that's one, no, nature of light, no? You cannot just really think of light as one continuous phenomenon in the universe, no, but it comprises of some smaller particles, no. So again, no, the photons, no. Here are the different spectrums, no, the varied, no, wavelengths of the spectrum of electromagnetic wave, no. So we have the radio waves, the microwave, infrared, no. So the wavelength there gets smaller and smaller, no, and it's probable, no, that it can, no, have, no, these lengths, no. So the length of a radio wave probably, no, will be in terms of the size of a building, no. So that's 1,000, no. So I think 10 to the 4 is 10,000, no, in terms of 10,000 meters, no. But as you go from left to my right, no, then the length of the wave there, the wavelength, no, becomes smaller, and it becomes, no, atomic in level, no. And again, the energy here, no, is kind of increasing, no? So as we go from left to right, the energy there tends to be increasing, no? Now again, these are other ways of looking at it, no? So the one in the middle again, no, which we call as the visible light, no, it has a color red, no, and maybe it ends with the color violet, no? So that's how long is the wave there, no? So one of this spectrum, no, is microwave. So it's a little, no, longer than radio, no, shorter than infrared, and this is its wavelength. It's a wavelength, no, and it is used for communication, for medicine, no, and for consumer use, like in our kitchen, no? We cook food, no, using microwave, but we can also use it in our cell phone, no? So the one in our cell phone, no, we send signals, no, in our cell phone, and it's the same kind of wave, no, that is, no, used, no, when we cook in our kitchen, no. So ways of applying, no, the microwave, no. Now the radio waves are those with the longest wavelengths, no, but with the lowest frequency, no? So its frequency is so few, no, because again, no, the wave is kind of very long, no. For you to create one complete wave, then it takes, no, some thousands of meters, no. So however, no, this is a useful wave for communication. So low energy waves, no, with long wavelengths, we hear words like FM, no? AM. This is when you go and listen to your radio, no? We use it in radar, no? So radar is a kind of device that measures speed, no? So how does it perform the measurement of speed? First, it throws the wave, no, out of a device, and then it strikes the object that is moving and returns back to the device that is used to throw the signal, no? So that giving off of the signal and returning, no, is a way of measuring how fast another object is moving. Like catching a car. I think in CPU, um, the university there has a radar. It has a kind of a radar gun that can determine those that are over speeding inside the university. I think the speed inside the university is only 10 kilometers per hour. So they can know, and they can probably document if you are traveling faster than that allowed speed. So that is if they will try to use the radar that they have. So again, so aside from using the radio waves in these mobile devices, we can also use it now for GPS, for even for again our radar. So radar is uh, used by policemen. You see that in some movies probably. But there are those that are used in detecting planes also, to know enemy planes, if there are those that are entering a country. So we have there also the MRI. So MRI is also a way of using radio waves. Together with I think some kind of a magnet. Infrared waves is felt like a heat, a form of a heat, and we can detect it probably to uh, to have reached us because it's in the form of heat. Now I think some special devices like night vision goggles, for those who fly, planes or helicopters, that does not have a night ano na, a night navigation equipment. They may probably wear some kind of a a night vision goggle. So for them to see, even at the in the dark. So they are composed of infrared waves. So military personnel, some special forces will probably use that night vision goggles. So again, it uses this wave of infrared waves. So infrared waves again, they have kind of very long wavelengths. That's why it can penetrate even through the dark. So we can usually feel the infrared waves. They are kind of warm objects. Here's a kind of an imaging device, probably a thermogram. The word is thermogram. So it's a picture that shows regions of different temperatures in the body. Temperatures are calculated by the amount of infrared radiation that is given off. Therefore, people give off infrared rays. So another way to know if there's still if there are living things that are still living things that are still alive by determining the amount of heat that they give off. So that's the concept of the thermogram. So visible light. So in our visible light, we know that red is one of the wavelengths there with the longest wavelength. And I think purple or violet is the one with the shortest wavelength. So we think that there were only seven. So we have there the Roy Biv, red, orange, blue, yellow. What's the sequence? Red, orange, yellow, blue, indigo. There's still green. Green, then blue, indigo, and violet. So we thought that there are only seven there, but in reality, there are actually a lot of combinations of colors there. But what is usually more pronounced are these seven colors. But actually, if we kind of mix them up, they say that there's a million other combinations there. But this right bib thing is the more pronounced, or rather maning mga distinct na mga colors git no. Usually no, red is a very striking color no, so it really catches our eye. Orange may also be a very striking color no. So usually no, rescue teams no, or the Coast Guard no, wear an orange suit no. So you will wonder why it's always orange, but orange is a color no, similar to red no, a little bit shorter in wavelength than red, but even at a very far distance no, if you are floating or you are already surviving no, in the middle of the ocean no, like let's say your ship no, drowns or your ship sinks no, and you are there no, floating, surviving, even at a far distance no, if there are rescuers, they can most likely notice the color orange no? Because orange again no, has a very long wavelength, and it can no, catch the eye no? So those are reasons why no, people no, that are seamen no, wear an orange suit no? So just in case they go overboard no? They fall no? They can still be noticed even at a very far distance no? So we have here the varied colors no? So we see this now, we call this as dispersion. So if this is a white light that gets into a glass no, that white light will now be split into several other colors no. But that's the time when you undergo no, you let no, a visible light undergo what we call a dispersion no. So from a glass no? So the principle there is of course refraction no? Light always bends no, because it changes its speed no, as it enters the piece of glass no. So the refraction of light here no, produces probably the seven varied colors of light. Next, we have violet waves no, and here is a tanning equipment. Maybe no, we Filipinos do not really not tan ourselves because most of us no, maybe no, would want rather not to have a fair complexion no? So if we are kind of darker in complexion, we drink a lot of medications just to make ourselves no, fairer no? So maybe no, we don't really use this no? But in some no, Caucasians no, they use this no, to tan themselves no. I don't know why no. Maybe no, but we have a different way of looking at things no, culture. But this is one device that they use not to tan themselves, and they use ultraviolet waves no. Now we also know that when there's too much ultraviolet waves, we can have some skin cancer no. So we have this lotion probably that protects us no. So there's a certain SPF value in some lotions that protects you from ultraviolet rays no. Well, there's the layer in our atmosphere called the ozone no, that prevents no, harmful amounts of ultraviolet rays to reach us no. So there was a time before that they say that the ozone layer is kind of damaged no, but I think it has repaired itself no, over the years no. So somehow no, the concern of the ultraviolet rays are not as crucial as what we have before no. But there was a time before that everybody was so conscious about the UV radiation from the sun no? But what I heard no, lately, that there's the repair of this ozone layer no? Now we can also no, have this skin cancer if we are overexposed to UV radiation. Now another way that we can apply UV radiation is for sterilization of some documents no, like right now there's COVID. They kind of scan things no, using ultraviolet waves no, to remove no, the COVID no, that is in the uh, document no. So when people no, use or sterilize things, they use the UV radiation no.